Question 4. The diagram shows a circuit used to investigate the resistance of a sample of a material. The diagram is not complete and the ammeter and voltmeter are missing. The first part, draw the symbols for the ammeter and voltmeter on the diagram in the correct places. So a voltmeter is always connected in parallel and around the component that you are investigating. So here we are investigating the resistance of a sample of a material. There is our material, so therefore our voltmeter must be around that material. Okay, so that's around there. The ammeter is connected in series around this circuit because it's a series circuit. So the ammeter position could be here where I've labeled it. It could be here, it could be here, here, or even here. So any point in the circuit, the ammeter is connected in series. So that's your second mark. The next part of the question is, how can the current through the material be changed? So let's have a look at this circuit. So how can we change the current in this circuit? This here is a variable resistor which allows a change in resistance. So if we change the resistance here, the overall resistance in the circuit will change and hence the amount of current in the circuit will change. So a variable resistor allows us to do that. So adjust the resistance on the variable resistor to change the overall resistance in the circuit, and that will allow the current in the circuit to change. Part B, material called conducting putty is rolled into cylinders of different lengths but equal thickness. So here we've got this material, is the conducting putty, and we can change the length of this material. And it's rolled into cylinders of different lengths but equal thickness, and the graph shows how the resistance changes with length. So we've got resistance on the vertical axis, length in centimeters on the horizontal axis. It says the current through 25 centimeter length of conducting putty was 0.15 amps. I use a graph to find the resistance of a 25 centimeter length of conducting putty. So if we look at 25 centimeters, there's no data there. So what we can do is use the data that's already been plotted and extrapolate that line and carry on, because the pattern, how resistance changes with length, should continue. So here we have a straight line, and so we carry on with that straight line all the way to 25 centimeters, go up and across at 25 centimeters, and that's 37.5 ohms of resistance in a 25 centimeter length material. So that's 37.5 ohms. Second part is calculate the potential difference across a 25 centimeter length of conducting putty. I know that the potential difference is current times by resistance. I know that at 25 centimeter length, the current in the circuit is 0.15. So the current here is 0.15. And I know the resistance of 25 centimeter length is 37.5 ohms. So that's 37.5. And we get a potential difference of 5.625 volts by multiplying those two values out using the formula voltage is equal to current times resistance, or potential difference is equal to current times resistance. And the next part of this question, a second set of data was obtained using a thicker piece of conducting putty. Both sets of results are on this graph. So what we have is the results from before, but now we've got results for a thicker piece. What we see that for the same length, we have a lower amount of resistance compared to before. The first part of this section is what is the relationship between the resistance and the thickness of the conducting putty? And what we can see is that the thicker pieces have a lower resistance than the thinner pieces. So at a given length, so pick whatever length, say 20 centimeters, the thicker piece, lower resistance than a thinner piece. So as the thickness increases, the resistance decreases. So we are looking for a relationship between thickness and resistance, not length and resistance. So name one error that may have reduced the accuracy of the results. Okay, so let's have a look at how we would have taken the results. So we are looking for resistance. So how do we get resistance from our experiment? We have voltmeter reading and an ammeter reading. So the resistance is there's a direct link. So resistance is equal to the voltage over the current. So if there's a error on the reading for resistance, how could we have got that? There could possibly be a error on the voltage reading, and it could be an error on the current reading, or maybe both. So there may be a random error on the voltmeter reading. They may have misread the voltmeter reading as well. Also, there may have been an error on the ammeter reading. They may have misread the ammeter reading as well. Okay, so those are your two sources of error. And then also can have a look at the length in centimeters. So misreading the length as well could have been a source of error. So misreading voltmeter ammeter reading or misreading the length. Question 5. Why did the student insulate the beaker of water? So what we've got as a setup is a student carried out an experiment to determine the specific heat capacity of water. This is a core practical for AQA. So figure 1 shows the equipment the student uses to heat the water. So they've got a heater that they've put inside of the beaker of water. They've got a thermometer inside the water as well, firmly insulated, and we can measure the amount of energy that we give to the heater using a joule meter, and the energy supplying the heater is from the power supply, which goes into the joule meter and out and into the heater there. Okay, so why does a student insulate the beaker of water? To reduce the energy transfer to the surroundings. There's always going to be energy lost to the surroundings, so it's to reduce the energy transfer to the surrounding. It's tempting to say to stop the energy transfer to the surroundings. However, it is very, very difficult to completely stop. All we can do is reduce the amount of heat transfer to the surroundings. Okay, so one hazard in this experiment is the hot water. Give one risk to the student caused by this hazard. As you have worked with hot water many times before, we know that hot water can spill, and it can spill on your skin and cause burns. So hot water spilled on skin can cause a burn. Part C of this question. So what's the resolution of the thermometer? The word resolution is the smallest measurement that you can make, the smallest division of that piece of equipment. So the smallest division is going up in ones. Okay, so 18, and then the next measurement is 19. So the resolution is going up in 1 degree at a time. So therefore, the resolution is 1. Question part D. The mass of the water is 0.2 0.2 kilograms, yet the reading is 0.26 kilograms, and that's because the mass of the beaker has been included in the mass measurement. So the mass of the beaker is the difference between this mass and this mass there, which is 0.06 kilograms. A calculation is required in part E. The energy transferred to the water is 26,400 joules. The mass of the water that's been heated up is 0.2 kilograms, and temperature increase is 30 degrees. Now, let's check if these units are all the right units we use when we use calculations. Yep, that's joules. No need of conversion here. That's kilograms. We use kilograms in formula, and we don't use grams, so that does not need converting. And degrees Celsius, so that is the correct unit as well. No need for a conversion there. So what is the unit for specific heat capacity? It is joules per kilogram per degree, and that is the unit. And the formula we need is the energy transferred is equal to the mass multiplied by the specific heat capacity multiplied by the change in temperature. This formula will be given to you on your formula sheet. You will need to rearrange it to find the answer for the specific heat capacity. So the energy is given to us as 26,400 joules. I've written that here. The mass is 0.2 kilograms. I've written it underneath the M. The specific heat capacity, C, is what we're trying to work out. So I've written C, multiplied by the change in temperature. That's the change in temperature, which is 30 degrees. I've written it here. Now the unknown is C, which is a specific heat capacity. Rearrange, and we get 26,400 divided by 0.2 times 30. And that gives us 4,400 as our answer. And that's 4,400 joules per kilogram per degree for the 4 marks.